when we think about black holes, something that may occur to you as you're thinking about this is, well, how can we possibly find a black hole if nothing can ever get out of one? If they are black, as their name says, and they are ridiculously small, only a few kilometers across in the case of most of them, how are we supposed to find one of these things? And certainly that's a difficult question. Basically, what we're going to do if we want to find a black hole is we're going to look for stuff that's falling into one. Because the stuff that's falling into one does give off light. And until it has crossed the event horizon, we can still see it. So what we need to do is we need to find stuff that's falling in. We need to see how fast it's moving and then maybe figure out something about the escape velocity. And if the escape velocity is bigger than the speed of light, well, we've got a black hole. So something we are going to need if we want to figure out speeds of things in space is the Doppler effect. Now, you've learned about the Doppler effect in physics class. This should basically just be a little review lecture for the most part. The Doppler effect, as you should remember from physics, is the change in wavelength if the source is moving towards or away from the observer. And this picture should kind of remind you of what happens. Some source of light is giving off radiation, and as it moves towards the observer over here, the waves get squished together because the source is moving in this direction. And for an observer over here, the source is moving away from him, the waves get stretched out. And that should be just something you remember from physics. So for something that it's moving towards, the wavelength gets shorter. For somebody that it's moving away from, the wavelength gets longer. And a change in wavelength, when we're talking about light, corresponds to a change in color. You may remember from physics we talked a lot about sound waves and the effect this has on sound waves. And for sound waves, the effect was to change the frequency or the pitch of the sound that was being produced. And so we heard those very strange sounds produced by ambulances and car sirens and so forth. But for light, that's a change in color. So when we're talking about the Doppler shift for light, we're going to be using the terms blue shift and red shift. Blue shift is a shift to shorter wavelengths for an object that's moving towards the observer, and the red shift is the shift to longer wavelengths for an object that's moving away from an observer. And this is going to be important because this is how we can measure the speed of things in space. We've got things in space, we want to know how fast they're moving, we use the Doppler effect. And so here's how the math works. Part of this equation, the sort of rightmost two parts of it, should seem familiar to you from physics. You should have seen this before. And I've added a third part back at the beginning. So here's what these variables stand for. Z is something called the red shift or the blue shift. It's basically the ratio of the speed of the source to the speed of light. It's kind of like the Mach number was for sound in physics. Z will be positive for a red shift and negative for a blue shift. And it doesn't have any units because it's like meters per second over meters per second, so that cancels out. V, again, is the speed of the source. So, for instance, there's a star that's moving around. The star's speed is V. We're going to make it positive if the star is moving away from us and negative if it's moving towards us. This is going to be something I'm going to try to trick you with on the test. I'm going to give you a speed, and you're going to have to decide if it needs to be positive or negative. And if you don't put the sign on it correctly, you may get it wrong. C is the speed of light. It's always 3 times 10 to the 8th meters per second. It's always positive. And then we have the two wavelengths, and this is another place a lot of people get confused. Lambda, without a little 0 on it, is the observed wavelength. This is what it appears to be. It's what the wavelength is that it's shifted to. It's not what it really is. It's not the wavelength that's being given off by the source. It's the wavelength that is observed by the astronomer. Lambda naught, with the 0 on it, is what we would call the rest wavelength. That's what it theoretically should be. Like if we had a source that was not moving, this is what we would measure. So it's also sometimes called the laboratory value or the theoretical value. That's what lambda naught is. Keep in mind that this is a 0, not a capital O. So some people want this to be observed because they think that stands for O. It's not. It's the wavelength when the speed is 0. That's the rest value. And you're not going to have to do any conversions. As long as these two wavelengths are in the same units, you can do the problem without doing any conversions. So that's relatively simple. Excuse me, hit the forward button 2 times. So let's look at problem 8 from your packet. We're given in this problem the redshift of some galaxy. In the next unit, we're going to talk about galaxies, and we're going to see that they are very frequently red-shifted and not blue-shifted. So that's our value of z. And it is supposed to be positive for a redshift, so I don't need to make anything negative. And the first thing I want to know is how fast it's moving. That's how fast is the galaxy moving. So I'm solving for v. I know that z is equal to v over c. So 0.25 is equal to v divided by the speed of light, which is 3 times 10 to the 8th. You've probably got that programmed into your calculator, and I'm not going to write out the number. So we can do this and solve for v, and it's 7.5 times 10 to the 7th meters per second. Positive because it is a redshift and moving away from us. Then it says, at what wavelength would you observe to see a line, this is like a spectral line, with a laboratory wavelength of 482 nanometers. So this is some spectral line, like of hydrogen. It's not H alpha, but it's one of those wavelengths. So we know, because of our study of spectra, we know what wavelengths we're supposed to see. But it's not going to be at 482 because it's shifted. So what we're looking for is the observed value, which is just plain lambda, knowing that lambda naught is 482. Now I can use any two pieces of that equation together. They are all equal to each other, so I can pick any part. So I could, for instance, just say that z is equal to lambda minus lambda naught over lambda naught. Oops, I'm not getting ahead of myself. So z is still 0.25. Lambda is what we're solving for. Lambda naught is 482. Here's a tip. I'm never going to make you solve for lambda naught. The algebra is too complicated, and we're just not going to go there. You can do it, but we're not going to. So I could do some math. 120.5 is equal to lambda minus 482. Add 482 to both sides. And so I get 602.5 nanometers is equal to lambda. So instead of being at 482 where we would expect it to be, based on the transitions in that element, we actually see it at 600 nanometers. Now, we can check this. This is longer than 482. And this was a redshift. We know that redshift means that the wavelength gets longer. What we observe is longer than what it should be, so something is correct. If we had mixed up lambda and lambda naught, we would have gotten something smaller, and our answer would not have made sense.